Yes, this question appeared in 2016 June exam. Okay, the question is this. The question is the first excited state of hydrogen molecule is the first excited state of hydrogen molecule is. Four options are given here. Singlet sigma gerade plus. Option B, singlet sigma ungerade minus. Option C, triplet sigma gerade minus. Then option D, triplet sigma ungerade plus. Okay. For hydrogen molecule, the electronic configuration, the ground electronic configuration. First I'll write ground electronic configuration. Right? Is nothing but sigma 1s 2. Okay. This is actually a gerade orbital. Sigma bonding is gerade orbital. So this is the ground electronic configuration of hydrogen molecule. First I'll show you how to find the term symbol for ground electronic state, ground configuration. Then we'll take the first excited state configuration for the excited state, and we'll find out the first excited, the term symbol for the first excited electronic state. Yes, how to do this? Listen carefully. I have already taught this. Okay. Anyway, we'll do it again. For electrons present in sigma bonding and sigma anti-bonding, right? For sigma or sigma anti-bonding, the lambda value, small lambda, this is called component of angular momentum, orbital angular momentum along the internuclear axis. This is 0 for electron present in sigma bonding and electrons present in sigma star antibonding. So now we have two electrons. Both the electrons are present in sigma bonding. Therefore, for electron 1, let the angular momentum be lambda 1. Then for electron 2, let the angular momentum be lambda 2. Add the two angular momentum, you will get what is called lambda. Okay, so what we get for lambda? This is 0 because both the electrons are present in sigma. For sigma orbitals and sigma star orbital, lambda value is 0. So this is 0, this is also 0. So lambda equal to 0. Lambda 0 means the term symbol is sigma. Okay. And I have also told you this, listen. For pi and pi star orbitals, lambda value should be either +1 or -1. For delta and delta star orbital, lambda value is +2 or -2. Okay, then symbols, listen, depending upon the lambda value, big lambda, okay, different symbols are available like atomic term symbols. If lambda is 0, the symbol is sigma. If lambda is 1, actually we take the magnitude of lambda. If magnitude of lambda is 1, then the symbol is pi. If the magnitude of lambda is 2, then the symbol is delta. Like that the symbol goes. Okay. Now, since lambda is 0, right? So it corresponds to a sigma state. And both the electrons are present in the same molecular orbital. You know very well, in same molecular orbital, the two electrons must have opposite spin. Okay, so total spin is equal to spin of electron 1, that will be plus half. Then spin of electron 2, which is present in the same orbital, so it should be paired, spin paired. Spins paired means one is plus half, the other spin should be minus half. So if I add these two, I will get that S is equal to 0. S is equal to 0. Therefore, multiplicity 2s plus 1. Put S is equal to 0 here. So I will get multiplicity as 1. So it is a singlet state. It is a singlet state. Okay. Then for sigma bonding molecular orbital. Okay. See, this molecule is homodiatomic molecule. So it has center of symmetry. It has center of symmetry. Okay. Now, with respect to inversion, whether the orbital is symmetric or antisymmetric. See, electron 1 and electron 2 both are present in sigma. For sigma orbital, sigma bonding orbital, okay, the inversion, right, is actually symmetric. Okay, so for electron 1, if the inversion of the orbital, if you carry out inversion on sigma orbital, it remains symmetric. Okay, inversion symmetric means gerade. So it has gerade symmetry. Inversion antisymmetric means it is ungerade. Okay, inversion antisymmetric means ungerade. Therefore, for the electron, since both the electrons present in sigma orbital is symmetric with respect to inversion. Therefore, for one electron it is gerade, for second electron also gerade, because both are present in the same molecular orbital. So gerade into gerade is gerade. Okay, then since the electronic state symbol is sigma, we should find out plus or minus. That is reflection about the internuclear axis we should see. For sigma orbital and sigma star orbital, as in sigma as well as sigma star, if you do reflection along the bond axis, since sigma orbital and sigma star orbital are cylindrically symmetrical, so if you do reflection along the bond axis, right, it appears as symmetric. So sigma orbital and sigma star orbital both are symmetric with respect to reflection about the internuclear axis. Symmetric means plus. So for electron 1 it is plus. Since electron 2 also present in the same orbital, that is also plus. Plus into plus is plus. Okay. Therefore, what is the ground state term symbol? Observe carefully. Ground state term symbol is, yeah. So let me write here. It is nothing but singlet, sigma, gerade plus. This is actually ground electronic state of the hydrogen molecule. Okay, this is the ground state term symbol for hydrogen molecule. Now, using the same idea, I'll show you how to calculate the or how to find the term symbol for the first excited state of hydrogen molecule. Okay, we'll do it. Listen. So, this is the electronic configuration, right? So, for the electronic configuration, sigma 1s2, right? The corresponding electronic state. For this configuration, the electronic state is actually singlet, sigma, gerade plus we found out. Just now we found out. The molecule is present in the ground electronic state. What is the first excited state? You know very well. Sigma bonding. The next immediate higher energy orbital is sigma star 1s. So from this orbital, one electron is excited or promoted to this molecular orbital. Now both the molecular orbital has one electron. This is actually the first excited state. We can also promote the electron to sigma 2s, sigma star 2s, sigma 2px. They are all higher energy excited states. They are also excited state, but they are all higher energy excited state. This is the first excited state. Clear? Now, what about the lambda value? Lambda value for this electron plus lambda value for this electron. If I add these two, I'll get what is called big lambda. Big lambda. I'll do it here. Okay, so what is big lambda? Big lambda equal to, listen, electron 1 is present in sigma bonding orbital. For sigma bonding, lambda value is 0. For sigma anti-bonding also, lambda value is 0. So this electron is present in sigma bonding. This electron is present in sigma anti-bonding. For both, lambda values are 0. So 0 plus 0 equal to 0. Lambda 0 means the symbol is sigma. So the first excited state should also have the same symbol sigma. Okay. Now we'll see so this is point number 1. Point number 2, we'll see the multiplicity. Now this electron is present in one molecular orbital, sigma 1s, and this electron is present in a different molecular orbital. In this situation, both the electrons may have same spin or the electrons may have opposite spin. There are two possibilities. Okay, so the possibilities are S is equal to, right? If suppose if one electron has plus of spin and the other electron also has plus of spin, both are having same spin. Okay, it may be upward or downward, whatever it is. Both are having same spin. Therefore, S is equal to 1. S is equal to 1 means 2s plus 1 equal to 3. So it is a triplet state. If both the electrons have same spin, same upward spin, then it is a triplet state. What is the other possibility? The other possibility is, isn't the electron present in sigma bonding may have plus of spin, and the electron present in sigma anti-bonding may have minus of spin. If it is like this, then total S value is 0. Therefore, 2s plus 1 equal to 1. I will get a singlet state. So what I am trying to say here is, for this configuration, this is an excited state configuration. Okay, this is an excited state configuration. Let me write this is sigma 1s1, sigma star 1s1. This is an excited state configuration. For this configuration, I have a triplet state and a singlet state. Okay, then third point. What about the inversion symmetry? For sigma bonding, see I have one electron in sigma bonding, the other electron in sigma anti-bonding. For sigma bonding, the inversion symmetry is Gerard. But the second electron is present in sigma anti-bonding. For sigma anti-bonding, the inversion symmetry is ungerade. Gerard into ungerade is ungerade. Okay, so the total inversion symmetry is ungerade. Then, since it is a sigma state, see I have sigma symbol. For sigma state, we should find out plus or minus sign. Okay, we should see reflection. Listen, since sigma bonding and sigma anti-bonding both are cylindrically symmetrical about internuclear axis, they are symmetrical with respect to reflection. So, the electron present in sigma is symmetric. The electron present in sigma star also symmetric. Okay, I just put plus. It's not plus 1, just plus. Plus into plus is plus again. Therefore, listen, for this configuration, we get two states. We get two electronic states. What are they? One is triplet, the other one is singlet. And you know very well, according to Hund's rule, singlet state has lower energy compared to triplet state. So let me write here, this is triplet sigma ungerade plus, and this state is singlet sigma ungerade plus. Okay. So for this first excited state configuration, two electronic states are possible. Among the two, the first one corresponds to the first excited electronic state. So this is the first excited electronic state term symbol, and this is the ground electronic state term symbol. Okay, take it. Therefore, the correct answer for this question is triplet sigma ungerade plus option D. Okay, so option D is the correct answer. Yeah, this question appeared in 2018 June CSIR JRFnet examination. We need to find out the ground state term symbol. See, they are asking ground state term symbol for B2 molecule. Right, so what to do? First write the ground electronic configuration. Okay, so the first step is write the ground electronic configuration. Okay, what is the configuration? See, boron molecule, each boron atomic number is 5. So B2 molecule has 10 electrons. See, B2 molecule has 10 electrons. Right, we need to fill up the electrons in different molecular orbitals, right? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Okay, after filling this, you know very well, atomic number of boron is 5, which is less than 7. Okay, if the atomic number is greater than 7, then the arrangement is different. Since it is less than or equal to 7, okay, atomic number, if it is less than or equal to 7, then pi orbital should come first. So I'll write here pi 2px, pi bonding, pi 2py, they are having same energy. Okay, bonding molecule, pi bonding molecule will come first, then sigma orbital. Okay, so I have only 10 electrons. I have already filled 8 here. See, 2, 4, 6, 8. I have 2 more. So I'll place 1 electron here and 1 electron here. This is the ground state configuration. If you have 2 orbitals with the same energy, you should fill the orbitals with 1 electron. Hund's rule, correct? So I just followed Hund's rule here so that I'll get the ground electronic configuration. Okay, now to find the term symbol, observe carefully. You need not consider the filled inner orbitals. Filled inner orbitals you need not consider. Just to focus on the outer orbital, which is partially filled. Okay. Actually, pi 2px, pi 2y totally they can accommodate 4 electrons. But now we have only 2, so it is partially filled. So I am going to focus on this. This is our goal. Okay. Now, what is the first step? Step number 1, lambda value. Okay, for electron present in pi 2px, for electron present in pi 2py. Observe carefully, since they are having equal energy, for one orbital, the electron present in pi 2px may have +1 and the electron present in pi 2py may have -1. Since they are degenerate, one have +1 value, the other one has -1 value. Okay, therefore, for pi 2px, we should find a big lambda. Big lambda is equal to lambda 1 plus lambda 2, where we have 2 electrons here. So, since the 2 orbitals, pi 2px and pi 2py, they are degenerate, lambda value for one pi orbital is +1 and the lambda value for another pi orbital is -1. So, if electron present in this pi orbital, that is pi 2px, then it should have lambda value +1, and if electron present in pi 2py, then lambda value equal to -1. So, I have one electron here and the other electron here. Therefore, lambda is equal to, for electron 1 it is +1 and for electron 2 it is -1. If I sum up these two, I will get the answer is 0. If lambda is 0, yes, you will get the sigma symbol. Okay, so ground state of boron molecule also have the same symbol sigma. Okay, then second point. Listen, the 2 electrons are unpaired. Okay, this electron is present in pi 2px orbital and this electron is present in pi 2py orbital. You know very well, we need to find out the ground state term symbol. According to Hund's rule, okay, if the 2 electrons present in the degenerate orbitals, if they exist as same spin, parallel spin, then they have lowest possible energy. Okay, therefore, the 2 electrons must have same spin to get the ground state, right? So, total spin equal to, for electron 1, I'll put +12. For electron 2 also, I'll put +12. Why? When the orbitals are degenerate, okay, first you should fill up each orbital with 1 electron having same spin. Then only you get the lowest possible energy. Okay, so S value equal to 1. S value 1 means multiplicity equal to 3. It is a triplet state. So, for B2 molecule, the ground state is a triplet state. Okay, so this is the second point. Now let me move on to the third point. Listen, that is, we should find out the Gerard symmetry with respect to the Gerard or ungerade with respect to inversion. We should find out. Listen, the 2 orbitals are degenerate, and you know very well pi 2px is present in one plane, pi 2py is present perpendicular to this plane. Therefore, if you place a reflection plane and if you do reflection, if one orbital is symmetric, the other one should be anti-symmetric. Okay, I am very sorry. I have given another, I'm sorry. Yeah. So first we'll finish off inversion. Okay, I didn't complete that. Listen, for inversion, right, pi bonding is ungerade, right? It is anti-symmetric with respect to inversion. Bonding pi orbital is anti-symmetric with respect to inversion. This is also bonding, so both are anti-symmetric, which means both the electrons have ungerade symmetry. So for electron 1, it is ungerade, and for electron 2 also ungerade. Ungerade into ungerade is gerade. So the term symbol, ground state term symbol has gerade symmetry. Then we'll see the reflection. Listen, pi 2px, pi 2py orbitals are present in exactly perpendicular to each other. If pi 2px present in one plane, then pi 2py is present, okay, right, exactly perpendicular to that. Therefore, if you do reflection, one orbital will be symmetric, the other orbital will be anti-symmetric. Therefore, for one orbital, if it is symmetric, I should put plus. For the other orbital, it should be anti-symmetric, so I should put minus. Plus into minus is minus. Okay. Therefore, the ground state term symbol for B2 molecule, diatomic boron molecule, is triplet, symbol is sigma, gerade minus. This is the ground state term symbol for B2 molecule. Okay. So the correct answer for this question is triplet sigma gerade minus option C. Okay.